Right, welcome back everyone. I hope you had a lovely Thanksgiving and managed to eat enormous amounts of food just like me. Okay, so today we're going to talk about past climate, and this is exciting for me because this is what my research is really on. Paleoclimate. Paleo is just a fancy way of saying past. Okay, and so we're going to spend a lot of today talking about how we know about climate from the past, how we generate records, what those records tell us, and how those records help us get at how climate can actually go sort of change through time. Okay, so there's a few announcements at the beginning. So course evaluations are open till Sunday. Thank you for all of those who already have filled it in. Please do fill it in if you haven't, because I do value your opinions. Concept maps. I keep getting lots of questions about concept maps. I have examples in my office, so if you would like to come and see those, you're very welcome to call past during my office hours on Monday, Tuesday, or Wednesday this week, and I'm happy to show you and talk to you about ideas. In discussions this week as well, the TAs will be getting you into groups and getting you to think of different connections that you can put on your map. So it's a good opportunity to go and work together and get some ideas then as well. Okay? It can be electronic, or it can be hand-drawn. It doesn't need to be on any particular size or anything else. Some people found that a slightly bigger piece of paper helped them spread things out a bit. And the important things are that it has to contain all four of those spheres: the biosphere, the atmosphere, the geosphere, and the hydrosphere. And the important bit isn't how you subdivide each of those spheres. It's really getting those major links. So for example, the biosphere takes in oxygen from the atmosphere and it returns CO2 to the atmosphere, okay? And that sort of respiration, and the opposite happens with photosynthesis. So these are the big connections between those, and that's what I really want you to include. And it is due by the final. I will not be accepting any after the final has begun. I don't care if you're late to the final or whatever else. I will not accept any that are given to me after that 1:30 on the Wednesday next week, okay? So if you want to hand it in early, if you're a bit scared you might forget in the stress of the moment, then you're welcome to call past my office anytime and drop it off. I'll put a box outside my office door. Does anyone have questions about the concept map? Yeah?
Can it be digital?
It can be electronic if you want. It's slightly sometimes more difficult to do, but if you can find software that does it, yeah. Any others? Okay. So extra credit. I've uploaded the extra credit whose deadlines have passed now. There's still the two movies that can be done until Sunday. So if you haven't done those and you would like to, please do that. But please don't upload them in Pages format because I can't open Pages documents. And regrades. So this is in my syllabus, but I wanted to remind you that if you think we've added up wrong, or if we've taken away a point that we shouldn't have, then it's really important that you get me to look at those before the final. There won't be any regrades after the final, and that's to do with a sort of academic honesty problems in the past. Okay, does anyone have questions about that? No. Well, it is the last week. Is everyone sad? No, clearly not. Okay, so, but that does mean that unfortunately it is finals time. So the final will be next week. It's going to be on the Wednesday in this room from 1:30 to 3:30. It'll be exactly the same format as before, but longer because we have longer, and I want you to show me what you know. Okay, instead of just one note card of notes, you are allowed one standard page, one-sided, one standard page of notes. Okay, so think about what's important to include on that. Okay, a study guide is available on the website. I might update it at the end of this week, but you can see what's on there, as well as answers to all the midterms, and if you go back into quizzes, you can see all the answers to the quizzes too. I'll be available for extra office hours in my office all of Tuesday, with a half-hour break for lunch, so if you have last-minute questions or worries, please do come see me then. And there will be a final review session. Unfortunately, again, it's somewhat late because we can't get a room for this many people. I'll be doing it because all my TAs are swanning off to a conference next week. So it'll be from 7 till 8 p.m. on Monday. Okay, and it's in a different room. It's in HSLH, and it's over by the Science Library. Does anyone have questions about the final? No. Good. Okay, in that case, let us get on with something slightly more interesting, which is we want to talk about climate today. And we're spending this whole week on climate because really it's one of those problems facing the world. And I think it's really one of the challenges that your generation in particular is going to have to come up with a way of sort of, if not fixing, of dealing with. And so it's important, I feel very strongly, that it's important that everyone has at least a sense of the science and the data that's sort of behind this sort of problem of climate change. So as a reminder, we have 5 factors that describe weather in our atmosphere, which is the state of the atmosphere at any one given time or place. And that's things like temperature, air pressure, humidity, wind speed, cloudiness, all that stuff we talked about way back now in the quarter. Climate, though, is an average of those. Okay? Climate is the average of, say, maybe 30 years of the temperature. Okay? It's 30 years of the wind speed or something like that. Okay? So, to make sure you're awake, first I click a question of the day. Which of these 2013 news stories, so A, B, or C, are related to climate rather than weather? So we've got A, which is the super typhoon that hit the Philippines very recently. We have our record-setting temperatures in California earlier this year. And we have our deadly tornadoes from a few weeks ago in November, actually. And they were the northernmost tornadoes ever in November. Is it D, which is all of them, or is it E, none of them? Okay, has everyone had a chance to vote? Who'd like to vote? Right, let's take a look. See if you fell for my question. Oh, the majority didn't. Well done, the majority. Okay, so 43% would be actually correct. None of those stories are related to climate rather than weather. None of those individual stories, okay? So yes, we had a heat wave this year and we set a few records. But that's one event. In order for that to be a significant climate change, we have to see a shift in the temperature of this region, that 30-year average, okay? If it's just bouncing around the average, if it's maybe bouncing up and there was an extreme and then it bounces down and it's cold the next year, that doesn't mean that climate is changing. That means that there was a severe weather event. Super Typhoon Haiyan, it may have been the strongest typhoon ever to make landfall. And yes, this is something that we might expect, an increase in intensity of hurricanes as our climate changes, as our temperatures warm. But that one individual event can't be attributed to climate change. And the same for the tornadoes. It's really unusual. We probably got the northernmost tornadoes on record in November. But individually, that doesn't say that the climate is changing. It just means that there was a severe weather event. And this is the problem with media reporting of climate versus weather. We get a cold winter and we go, climate change is off. No, it's cancelled. It's not happening. Because we're looking at weather events on a background state. Our background climate is changing. But we still get weather events around that. Okay, so hopefully that's a clear point for everyone now. So when we talk about our climate system, it's quite a complicated concept to get across. Because it's not just like temperature, how warm it is. Our climate system is actually a really complex set of interactions between different things. And this is sort of the culmination of what we've been doing all quarter, because you can see that we have the lithosphere and the geosphere, which is sort of having volcanic activity, which releases aerosols into our atmosphere. And our atmosphere, say the clouds and the dust and the gases, will absorb or reflect different amounts of energy coming from the sun. We have the biosphere, which affects things like the albedo. It affects things like the exchange of energy and water between the atmosphere and the land. And then we have our oceans, our hydrosphere, and that big overturning circulation which can transport heat around the world as well as storing enormous amounts of carbon and energy. So you can see that there's actually really complicated sets of interactions that make up our climate system. And that's one of the reasons why it's so difficult to sort of accurately say with complete certainty what it might do as we change one or more aspects of that. Because we're messing with a lot of different components. We're changing the composition of the atmosphere in terms of the gases. We're changing the aerosol content. We're changing the biosphere cover over a lot of the land surface. We're changing the albedo. So all of these things are changing, and so it's really difficult sometimes to grasp how these will respond. So this is where past climate comes in, paleoclimate, what I do. Because what we want to know is, well, we can see that climate is changing today. Is that anything particularly rare? Can we see that climate has changed differently in the past? If so, on what sort of scale? Is what we're seeing today really that unusual? Or was it maybe 300 years ago, did we see the same thing? How and why? So, okay, we're seeing that our climate is changing. Well, how can we say, sort of, what is the most important thing about why it's changing? What's the main cause for that change? And then thirdly, rather, if I can count, then it's actually how we test our climate models. So we have these quite complicated climate models that we run to predict what might happen in the future. How do we know they're telling us anything even vaguely right? We actually test them by seeing if they can accurately reproduce what we know has happened in the past. So that's why past climate data is so helpful, because if we run our model for the past and we see something really different from what was happening, we can say to each other, well, we must be missing some fundamental part of the physics or the chemistry, or something in our model isn't quite right. And so that's a really important way that we use information about the past climate. Okay, so how do we know that our climate is changing, and how do we know how it has changed in the past? Well, first of all, we can measure it. And so certainly from the 1800s onwards, we have, somewhat patchy at first, but as we move towards the present day, a better and better idea of climate. And that's from instrumental records. So for example, here's our little temperature record from 1860 to 2000. And you can see that over that time, there have been little wobbles, but overall there's an increase in that temperature. Okay? But the problem is that that's really only the last 200 years. How do we go about actually looking at what climate was like thousands of years ago, or even millions of years ago? Well, first of all, the most obvious one is we can look at the geologic record. If we can find sort of crocodile fossils in what is now the Arctic, then it gives us an idea that somehow climate must have been very, very different in the past. So fossils are a really nice way of giving us a sense of, say, how wet an area was, or how dry an area was, or how cold or warm. And then, of course, we have landscape features. So do you remember when we talked about ice and the cryosphere, we talked about Yosemite Valley and how this big, enormously steep, wide valley was carved by big glaciers moving through it. So that gives us an indication that at some point in the past, there must have been much colder conditions in this part of California, which allowed these big glaciers to form. And it's the same if you drive out into the desert, you can see lots of dry lake beds everywhere, which indicates it must have been wetter here in the past as well. So these are pretty good sort of qualitative measures of our climate system. They can say, well, it must have been somewhat warmer or a little bit colder. But they're not so good at really quantitative, saying how cold it was or how warm it was or how wet or dry. For those, we actually rely on what we call proxy records. So just like you can vote by proxy, as you can send someone else to vote for you, proxy records are something that you're not directly measuring the temperature, but something else is sort of recording that temperature for you. Okay? And our proxy records are records of natural events that are controlled by or reflect some aspect of climate. Okay? And we're going to think of some examples here. Okay? The first one is, I think, one of the most fascinating ones, which is our cultural records. So, for example, in Europe, we can find records of things like the grain prices going back hundreds of years. And you can see that in all of the countries, at a particular, two particular times, the price spiked. And what that can tell us is probably something about climate. Why do you think we might want to look at 4 countries rather than just, say, the UK or France? What else might affect grain prices in a country? War, conflict, social changes, whatever else, political changes. So these things might also affect it. So in order to check that it's climate, then we look at lots of different countries and we can get a sense of whether that's the case or not. Okay? So things like that. Off Iceland, they have a record of how many weeks per year that there was sea ice in contact with the coast, because then they couldn't go out fishing. So you get Egyptian records and Chinese records going back sort of hundreds and hundreds of years about how wet areas were or big events. So cultural records are really cool, and we're trying to find ways of exploiting those more. And then we have natural records. And this is something that everyone is familiar with, because everyone has seen at some point a tree stump. And who has never tried counting tree rings? Okay, so good. Most people have tried counting tree rings. Okay, and everyone knows that you can count tree rings and you can get back to how old the tree is. So hopefully everyone's seen that Gary Larson cartoon where they cut the tree down and they say, oh look, this guy's like 10,000 years old or something. We don't cut down trees to take tree cores, by the way. People get very stressed out about this every year. This is a tree that was already being cut down. In reality, if we want to go out and study tree cores, we take a tiny, tiny, tiny little tube and we insert it in and we extract a little core that way. It's very rare that we actually chop down a tree to get at the tree core. We're not that destructive, okay? And so we can get records from tree rings, because not only can we count the rings and get a sense of how old they are, but also if you look at these tree rings, and if you look next time you see one of these, then the width of these rings varies. Why do you think the width of the tree ring might vary? It might have grown more in a certain year, and why might it have grown more? Perhaps it wasn't limited by water, by temperature, by one of these things that otherwise would limit its growth. So narrow rings might reflect years that were not so friendly for tree growth. It might have been too cold or too dry, and then sort of fatter years might have been much happier years for the tree when it wasn't as limited, okay? Does anyone know how old bristlegone pine trees can get? These are your other native trees in California. Thousands and thousands of years old, okay? These can be sort of 5,000 years or older. And so we can get really nice long records from tree rings, and we can also piece them together to get further and further back in time. So that's one that you're familiar with, and I think it's pretty easy to get a sense of how they could be used. The second one is something that we've used a lot, especially if we're going a long, long way back in time, and that is ocean or lake sediments. Okay? And so you can see that we have these big ships, and Alicia, our TA, has been out on these big ships, and they take sediment cores. They drop these sort of big cylinders down to the bottom of the ocean, and they take a core of sediment. And what they can look at is they can look at things like whether there are little sort of fossils in there. They can look at the chemistry of those fossils to get at things like water temperature or salinity or the nutrient content even. Near lakes, we could look at pollen. So my little cartoon here shows that if we have a pond or a lake, then pollen from the nearby vegetation will blow into that lake. If we see a change in climate, we might see that these trees might disappear. We might have grassland instead, or sort of tundra even if it gets really cold. And so the types of pollen that you get in your lake will change. Okay, so if you can create a time scale for this, then you can get a sense of how climate has changed from how the pollen has changed. Because each different species has a different shaped pollen grain. Did you know that? It's a weird thing to know, but some people spend their whole PhDs picking apart pollen grains. Would drive me crazy. Okay, so lake and ocean sediments allow us to get back millions and millions of years in terms of reconstructing our climate. Ice cores. Who hasn't heard of the ice core records? Hopefully, more or less everyone has, because they're really important. Okay, I think they're one of the biggest contributions of my field, paleoclimate, to the world, really. And what it is we can go out into Greenland, into Antarctica, where there's sort of kilometers thick ice, which is basically just snow that has piled up year on year for maybe up to 1 million years in Antarctica, for maybe 120,000 years in Greenland. And what we can do is we can take a core, and we can measure both the chemical components of the ice, which can give us a temperature record. But also, if we look at these ice, this is a slice through that core, we can see lots of really tiny little bubbles. And do you remember when we talked about snow, and I said if you didn't like someone, you packed down that snow really tight and threw it at someone? As you get that snow, it's full of lovely, soft sort of pockets of air. And over time, that snow gets compressed by overlying snowfalls, but that air gets trapped. So that air that's trapped in the ice is actually little bits of the atmosphere from however many hundreds of thousands of years ago it was when that snow fell. So I think that's really neat. And so I have a question for you. So I'm going to give the game away if I say too much. So I'm just going to ask the question. So think about your definition. Okay, I think that's more or less everyone. So let's take a look and see. So it's a difficult question to answer, but remember a proxy record is actually saying it's not directly recording the temperature, something else is being affected by temperature and therefore being recorded. But in this case, we've got actual real bubbles of the atmosphere. If we melt that ice, we get out real samples of the atmosphere from 100,000 years ago. So it's not really a proxy, is it? We're actually directly measuring what was in there to begin with. So I put it under my proxy list, but perhaps you should be calling me out on this and saying, well, actually, it may not be a proxy after all. So, unfortunately, our lab, which looks at ice cores, doesn't have enough for me to pass this round, but I brought you some pieces of the Antarctic ice core. Okay, so this is snow that fell on Antarctica maybe 5,000, 6,000 years ago, and was drilled up a couple of years ago at the West Antarctic ice divide, or ice sheet, okay? And what you can do is, at the end, because I can't do it now, unfortunately, come down to the front and you can hold this stuff up to the light and you can see the individual bubbles in here. And that's something that's different. If you try and do that in your freezer, everyone says, oh, you faked it, didn't you? It's not possible to fake it. If you try this in your freezer, all the bubbles disappear. It's really the only way that you can get ice bubbles like this is by getting it from an ice core, okay? So come down and have a look at this at the end. They've got 1,000-year-old pieces of ice from Antarctica, which is very cool, I think. Okay. So, what do those nice ice cores actually show us? I've said that they're really important. Well, why? Because we can get records like this from them, okay? So this is Antarctic ice core data, so possibly bits of that. That bit that I showed you is probably just a few thousand years old. We can actually go back nearly 800,000 years in Antarctica. So we can get a record of what was in the atmosphere for 800,000 years. And I think that's just amazing. No one else looks excited, but I think it's really amazing, okay? And so in that red graph there, you can see CO2, carbon dioxide in parts per million. Okay? And you can see that we have these sort of every 100,000 years or so, we see this pattern. We go from sort of fairly low carbon dioxide levels of maybe 200 parts per million or less. And then every 100,000 years or so, we go up again to maybe 250, up to maybe even 300 parts per million more recently. Okay? And these are our glacial, interglacial cycles. When that CO2 is high, we see much warmer conditions on the planet. We today are in an interglacial period between two ice, more ice common periods, okay? And not only that, but you can see things like the amount of dust in the ice, and that dust gives you a sense of how windy it was. And you can see that when it's cold, when we have low CO2, it's really dusty in the atmosphere as well. And then you can see at the top, we can see a reconstructed temperature record, again from the ice. And what should leap out at you is that it's not a perfect match, but there's a really very close tie between that carbon dioxide level and the temperature at this site. And that's something we see on Greenland too, okay? And so this is sort of the driving force behind our idea that changing CO2 levels will change temperature. Okay? And you can see that included on our red sort of graph here. We get to the end, and that red line shoots up. And that's because today, having varied between maybe 200 or 180, maybe and 300 for the past 800,000 years, and probably much longer than that, we are now at 400 parts per million. Okay? So we're changing the Earth very quickly out of balance. Okay. So, and lastly, there's a whole bunch of other stuff that we don't have time to go into, unfortunately, but things like cave deposits, the chemistry of those. We have corals, and I always like bringing this along because it's very cool, okay? Has anyone ever been in a cave? A few people? And you've seen things like this, stalagmites, and these grow because every sort of now and then a little drip full of CO2 will fall from the ceiling, and then it falls onto here, and we get calcium carbonate precipitating out. And again, the chemistry of these reflects both temperature, but also things about the rainfall, so where that rainfall came from, perhaps, or how much rainfall there was. So these have been really useful in parts of the world for reconstructing temperature. Starrell, this is her Ph.D., she's working on one of these from Crystal Cave up in Sequoia National Park to look at storm patterns for the last 1,000 years or more. And she's seeing some really interesting things. And this one's from China, and this one was used to reconstruct things like monsoon strength for thousands of years. And that's because you can see on the inside, those of you at the front, if the people at the back want to see, they can come at the end. You can see that it's layered. It has layers, just like tree rings. It grows incrementally, and we can sample the chemistry, and we can get back a sense of how the climate has changed in this particular location. And they're also really very beautiful. Okay, and heavy. So things like corals and anything that grows with layers can help us work out what climate has been like. Okay, so we have lots of ways. We're not just making this stuff up. We know that climate has changed, and we can get a sense, therefore, of whether our change now is something unusual. And it turns out that as we look back, even just at the last 500 million years, which remember is that interesting time when there's lots of life around, then you can see that we've had times which were cold, which were sort of down the page, and you can see that we have glacial periods, so periods when there was ice on Earth, significant amounts of ice on Earth, are marked in blue. But you can see that there have also been times when it's been really actually much, much hotter, when in fact it's been so hot that there hasn't been ice on Earth at all. So for example, if we look most recently, in the last 50 million years or so, we have ice on Earth, if that's to the glaciers or if that's ice sheets. But maybe 100 million years ago, the Cretaceous period when we had dinosaurs wandering around the Earth, then actually it was so hot back then that there weren't big substantial bodies of ice around. Okay? So we're going to look in more detail at those. So we can see that climate has changed, and by looking at climate records on different time periods, we can get a sense of why that is. So we know that climate has changed. Now we want to ask the question, why? And this is important for us, because if we understand how we can have seen such big changes in the past, that might give us a clue as to how our climate might change in the future. Okay, so first of all, and this should ring a bell, because we're going back to really what we talked about, I think it was in lecture 4, like way, way back in the quarter, when we talked about what sort of factors control our planetary temperature. And so our first one was solar variability, solar strength. And remember, we talked quite a bit then about how over billions of years, our sun has actually been getting more luminous. It's been giving out more energy. Okay? But it's not just over billions of years that solar variability changes. We also see even smaller timescale changes. So on an 11-year cycle, we see what we call the sunspot cycle. So it's a time when, if we have lots of sunspots, actually the sun is more active. We're getting more radiation than when we don't have sunspots. Okay? And you can see that they counted the sunspots back maybe sort of 200, 300, 400 years. And you can see that on top of that 11-year cycle, we also see much longer-term sort of wobbles in how much solar output there was. And in particular, around this time, we have hardly any sunspots at all. And it's a time called the Maunder Minimum, and it actually coincides with what we call the Little Ice Age, a time when Europe especially was extremely cold. We used to have ice fairs on the Thames, whereas today it hardly snows at all. Okay? And so it appears to us by looking at these records that even small changes in solar sort of luminosity actually have relatively large changes in terms of Earth's temperature. Relatively large temperature changes. And it's really unclear to us right now still how exactly that happens. And so it has to be some sort of feedback loop connected in here. And so maybe it's clouds, something like that. We're putting lots of research money into studying how clouds might change. But one important thing to note, and I'll show you this on Wednesday as well, is that even if we can see wonderful correlation with, say, Earth's temperature and solar variability in the past 1,000 years or so, in the past 30 years, our solar sort of output has been going down and down and down, and our temperature has still been going up and up and up. Okay? So there's really strong divergence in the last 30 years especially that can't explain our most recent climate changes. So the second thing that could change our climate are things like the distributions of continents and mountains. First of all, they drift over millions and millions of years, so this is very long-term changes. But they can cause changes, for example, because if we have a big supercontinent, we're going to have very different climates distributed over that supercontinent than we would if we have lots of little continents around the world. And that's especially true if we have continents over the pole, or if we don't. And then the other thing that these drifting continents can do is they can change our big atmospheric and ocean circulations. So again, we can start seeing changes to climates over the Earth. Okay, so the third thing, so now we're getting on to albedo, which is another thing you should remember from way back. We talk about it a lot. So things like surface changes. So over long periods of time, things like continent position, growing ice sheets, but also shorter timescales like expanding forests or deserts, sea level rise or fall, snow. Snow particularly sort of can affect our planetary albedo. So all of these things can come back and affect our temperature. Then we have greenhouse gas concentrations, which we've talked about a lot already. And so you can imagine that carbon dioxide and methane are our big greenhouse gas concentrations that vary significantly. And so on million-year timescales, you can imagine if we have more volcanic activity for a certain reason, we might have more greenhouse gases in our atmosphere, or if we have more weathering. For example, when India smashed into Asia and we had the Himalayas starting to be uplifted, then we got much more weathering, and we saw a dip in our CO2 levels in the atmosphere. And then on shorter timescales, we've got all of those things we talked about for the carbon cycle very recently. We have the biosphere, we have oceans, we have sort of us burning fossil fuels. Aerosols, okay? We talked about this when we talked about mass extinctions. That aerosols are complicated. We can have two different things going on. So some types of aerosols will actually dim what we call sort of dim the Earth. And that means is that they're reflecting away more of that incoming light before it can warm us up. Or they could actually absorb more of that outgoing radiation in the same way that greenhouse gases do, and so keep us warm. So it's actually what type of aerosol you have in the atmosphere and also where it is in the atmosphere can have a strong impact on our temperatures. And then everyone's favorite thing, and I'm going to spend a while on this because it's a little bit complicated. So if your neighbor is asleep, give them a bit of an elbow and wake them up because they're going to want to listen to this. Okay, so this is the challenging bit of today. It is called Milankovitch cycles, and it's really the reason that we have that amazing 100,000 year cycle in our ice ages. This is what explains that, okay? So Milankovitch cycles are a result that our Earth's sort of orbit around the sun actually isn't constant all the time. There's certain sort of patterns that means that it changes. And the first one that's most easy to remember, I think, and easiest to imagine is what we call eccentricity, which is basically how elliptical our orbit is. So do you remember, our orbit isn't perfectly circular today. And in fact, it varies from being slightly more elliptical and slightly less elliptical, slightly more and slightly less. And it varies on a 100,000 year time scale. Okay? We have another one. We have the obliquity cycle. And this is a cycle that happens every 40,000 years, and it's to do with the tilt of the Earth. So I told you that the tilt of the Earth is maybe about, I don't know, 23.5 today. It actually varies. It sort of tilts a little bit further over, and it tilts a little bit further back up again. And it does that every 40,000 years, okay? And that change in the tilt affects how maybe strong your seasons are, because if you're tilted further over, you're going to get warmer summers and then colder winters, okay? So obliquity is this sort of wobbling backwards and forwards of our tilt. And then everyone's favorite one, okay? And this is a challenge, and I'm going to make sure you guys get this today. It's called precession, okay? So do you remember I said that we have our tilt, okay? And as our Earth is tilted, it's tilted towards the sun, actually when we're furthest away from it, okay? Which is a funny thing for the northern hemisphere, because you think if we're further from the sun, we must be colder. And actually that's not true, because we're tilted towards the sun when we're furthest away. And as we orbit around the sun, that tilt doesn't change. So by the time we get around here, the northern hemisphere is now pointing away from the sun, and so we have winter. And then that tilt doesn't change, it comes back around until we're back where we started with. And that's what I told you earlier, right? Well, in reality, that is true for each individual year, but actually that tilt does that, okay? So, and this sort of cycle is every 23,000 years. So you see my little diagram here, watch those yellow lines for my Earth. So today, that's the way we're tilted. 11,000 years ago, and 11,000 years from now, we're actually going to be tilted that way, okay? So now, in the northern hemisphere, when we're furthest away from the sun, we're tilted away from the sun in our winter. And when we're closest to the sun on our elliptical orbit, the northern hemisphere is tilted towards. So again, it's not changing as we go around. That tilt is constant in that year, but over that 23,000 years, it actually changes, okay? Everyone looking a little bit stunned. So, prove to me that you can understand this. This is my really evil eye-clicker question of the day, okay? Speak to someone from the atmosphere class, because we did this, okay? So, 11,000 years ago, think about what the northern hemisphere is like today and what it would be like in the past. What would the seasons have been like? So I'm going to give you a couple of minutes to consult with your neighbor, and then we'll come back and I'll ask the question. Okay, I'm going to go ahead and ask the question, and we'll see if we have a consensus. I think that's more or less everyone. So let's see what our answers are. See how awake everyone is today. Ooh, oh my goodness, you guys are brilliant. I think this is the best result I've ever had with this question. Okay, so yeah, either that or I'm just getting better at explaining it, which I don't think is the case. Okay, so you're right. Okay, so if we go back, we can see that today, our summers are actually when we're furthest away from the sun. If we actually change that and have our summers when we're closest to the sun, we're going to get warmer summers. Okay? If we today have our winters when we're closest to the sun, if we then, in reverse, have our winters actually when we're furthest away from the sun, we're going to get colder winters. So absolutely, so 11,000 years ago, our seasons in the northern hemisphere were more extreme. In 11,000 years' time, our seasons will again be more extreme. Okay? Great, oh my goodness, you guys are great. Okay, I don't mean to sound that surprised. Okay, so those are our Milankovitch cycles, and they're really amazing. When we found this, or Mr. Milankovitch found this a couple of hundred years ago, I don't think it was quite that long ago, but it really explains so much about the climate that we couldn't really understand before. Because if we add up all those different cycles, and we look at individual latitudes on Earth, it really has a big effect on how much of that incoming radiation we see, due to our tilt and that beam spreading and the atmospheric sort of deflection and everything else. So you can see that if we add up our 100,000 year cycle, and our 40,000 year cycle, and our 20,000 or so year cycle, we get this really weird pattern, wibbly wobbly pattern, okay? But we see in our isotopes, so in oxygen isotopes, which can give us a sense of temperature or how big our ice sheets are, we can see that same sort of 100,000 year pattern. We can see similarities there. But it's not exact, is it? So our 100,000 year cycle in our record, we saw it in our ice core record, is actually much stronger than it would seem on here. If it was only to do with Milankovitch cycles affecting how much incoming radiation we got, we wouldn't expect to see such a strong 100,000 year cycle in our ice core records, in our sediment records. In reality, what's happening is we have feedbacks, okay? We have a whole bunch of feedbacks going on. And I was going to get you to sort of guess, or not guess, but tell me as many as you can think of, but I don't think we have time, unfortunately. So here's my list, okay? So we have our ice albedo feedback, and that's an important one if we're growing big ice sheets and shrinking them back again. We have water vapor and clouds. A colder climate can contain less water vapor. We have sort of the temperature chemical weathering feedback. When it gets colder, we have less chemical weathering, and so we can build up more CO2. We have things like our ocean temperature feedback. That was everyone's most hated question in the quiz this week. We have our atmosphere biosphere feedback, and then we have our things like our permafrost feedback on carbon gases in the atmosphere. And so a lot of these feedbacks come back to things like greenhouse gases in our atmosphere, and really that's the feedbacks that are having a strong impact on that, on top of that Milankovitch cycle. Okay, so here's 5 minutes of climate history on Earth. So the Middle Cretaceous, 100 million years ago, if you lived then, you would have been eaten by dinosaurs, but you'd also have been much warmer. Coral reefs grew right up to the poles. We also had things like alligators, crocodiles, sort of cold-blooded things right up to the poles. We had sea level that was 100 to 200 meters higher than today, so that's like 100 of me stacked on top of myself. Global temperatures were maybe anything from 6 to 14 degrees warmer than today, and that meant that the temperature difference between the pole and the equator was a lot less, and so we didn't get as much atmospheric and ocean circulation. So why was it so different? Well, things like the continent positions changed our albedo, and also the circulation of our oceans, but also our carbon dioxide levels were anything from 8 to 10 times higher than they are today, maybe something like 3,900 parts per million. So it's a very much warmer time in Earth's history. But ever since then, we've been gradually cooling off. So this is sort of from 50 million years ago at the bottom to 0 to present at the top. And don't worry about all of the funny names up the side. They're just the geological eras. But you can see that we have surface ocean temperature here. Back 50 million years ago, our average surface temperature was more like 20 degrees Celsius. which is way warmer than what it is out there today, way warmer, okay? And so you can see that through time, we had a gradual cooling. And as we cooled off, you can see that maybe 35 million years ago, we started building up glaciers in Antarctica. As we cooled some more, maybe around sort of 3 million years ago, so actually amazingly recently in our Earth's history, we got ice sheets building up on, in the northern hemisphere as well, up on Greenland, okay? And so you can see that we're actually really in quite a cold period in Earth's history, okay? That doesn't mean that warming isn't going to significantly affect us, but if we look at Earth's history, we're quite a cold period. And why was it cooling down like that? Well, first of all, we were changing our continents around, and that changed our ocean and wind currents, but also, most importantly, we were gradually reducing the amount of CO2 in our atmosphere. Okay, so if we look at the last 2 million years, you can start seeing really crazy stuff. So here's our cold glacials in blue, and our nice warm interglacials in yellow there. And you can start to see these Milankovitch cycles. Now that we're zooming in much more carefully at a smaller time period, you can see that we have these massive wiggles backwards and forwards. And these are every 40,000 years down here, and then maybe 1 million years ago, we switched into these 100,000 years. They're both Milankovitch cycles. Why we switched at that point is a bit of a mystery still. I love finding these mysteries. But our climate changes, we can definitely say Milankovitch cycles affect the timing of those changes. But in order to get the extremes, we need extra feedback loops to do with things like carbon dioxide in our atmosphere. Okay? Last interglacial, so the last time we were this sort of warm was maybe 120,000 years ago. And at that time, maybe our temperature was probably pretty similar today. Because of the changes in our orbit, the northern hemisphere was slightly warmer, maybe 1 to 3 degrees Celsius. And so this is a really interesting time to look at if we want to try and see what our world might be like in the next sort of 50 years. And the interesting thing about this was that sea level at that time was 6 meters higher than today. So that's 4 of me stacked on top of myself, okay? And that's what the beach level was, so where you park up in sort of Crystal Cove Park, okay? And this is that ice core record again, showing how closely that CO2 and those temperatures are linked. Then we have our last ice age, our last glacial maximum. So the last time the ice ages, or the ice sheets were at their maximum extent. And it was a really different world, and this is only 20,000 years ago. It's remarkably recent. So then our temperatures were maybe 4 to 10 degrees lower, and they were really unstable. They swung really quickly from one extreme to another. The ice was actually advancing at 25 to 100 meters per year, and that's really fast. We had maybe 1 kilometer of ice over a lot of our northern cities. And that meant that if we had all of that ice on the continent, our sea level was actually 120 meters lower than it is today. Okay? We had lots of permafrost at low latitudes. We had really dry, dusty atmosphere. Remember those dust peaks in our ice core record. And we had big lakes. The Salt Lake is now a remnant of one of those big lakes. Okay? And then lastly, our last 10,000 years, we're back into an interglacial. And that really stable climate, you can see how constant that red line is for the last 10,000 years, is what has allowed us to develop agriculture and civilization. Okay? But the next question is, what is going to happen next as a result of this? And that's what we're going to talk about on Wednesday. Thanks, guys.